So we said that the smoking gun for human impact on climate is the instrumental temperature record and the warming that it's shown since the 70s, and that the models are able to explain that warming if you tell them about rising greenhouse gas concentrations, and they're not if you don't. But that isn't really fair, because it makes it seem like the whole thing, our confidence in it, is based on the models. And in fact, the reason why I personally believe that the models know what they're talking about comes from comparisons also with climate changes in the deeper past, what are called paleoclimatology constraints. If we look back further in the past, we have much larger changes in Earth's climate to work with, but unfortunately also the uncertainties become bigger as well. So it's sort of a trade-off in that regard. So one of the most important findings in paleoclimatology is the close link between atmospheric CO2 concentration and ice volume and temperature going back through time through the ice ages as revealed in the ice cores. So this plot, we'll talk more about it in coming lectures, but it demonstrates a very, very tight correlation between CO2 and temperature. Makes it clear that there is a CO2 impact on Earth's temperature. And in fact, what we'll see is that we can quantitatively boil this down and try to derive a value of the climate sensitivity, delta T2x, the amount of warming that we expect from doubling CO2. And we get pretty much the same answer from looking at these CO2 and temperature fluctuations as we do from looking at the recent instrumental temperature record. So it gives us a separate sort of independent check on the role of CO2 in Earth's climate. The reconstruction of Earth's climate in the past is based on what are called proxy measurements of various climate parameters, mostly temperature, but also other things like water availability or winds or things like that can be pulled out from proxy measurements. It's a proxy because we don't have a thermometer from thousands of years ago to actually measure the temperature, so we have to come up with other clever things that we can use to guess what the temperature was, and we do the best we can at that. It's certainly not as good as having a real thermometer, but we can get a lot of mileage by looking at things that we'll talk about, like the widths of tree rings of old fossil logs from ancient trees can tell us about temperature and drought. Borehole temperatures are temperatures down inside an ice sheet or a big rock or something like that that we can use to back out changes in temperatures in the past. Basically, in general, a lot of the paleoclimate records come from ice cores that accumulated in Antarctica or Greenland or on the tops of mountains, little mountain glaciers, and also sediment cores from the ocean and from lakes. So let's hear about some paleoclimate proxies. Tree ring width is one of the best ways of piecing together climate changes of sort of the last 1,000 years or so. So a tree has a seasonal cycle of growth if it's growing in a place that has a seasonal cycle in the weather. So this method doesn't work in the tropics where it's sort of warm all the time. It works in the higher latitudes where you have a distinct summer and winter. So most of the growth happens in the summertime, and in the wintertime you get a layer that has a different color, and so you can count the rings in a stump, and each one of those rings corresponds to a year. So how wide the ring is in a particular year depends on a whole bunch of things. It can depend, in addition to temperature, it can depend on the availability of water, it can depend on sunlight, the age of the tree, things like that. And so there's a lot of noise in this method that has to be averaged out or has to be gotten rid of in one way or another. So you get the primary calibration of tree ring width to temperature by comparing it with the instrumental temperature record, the time span over which there are measurements from thermometers. And that can give you a calibration that you can then project further back into the past to say, well, if the width was here, then using that same calibration, the temperature must have been there. And then the way noise is further reduced is by looking at spatial patterns of these records from all around the world. This is a terribly drawn map, but you can use your imagination and figure this is South America, North America, and whatnot. And if you have a distribution of tree ring records that cover the whole surface of the Earth, or a large fraction of it, you can compare the variations that you see in the tree rings with patterns of variation like the El Nino cycle. So from the instrumental record, we have some idea that when the Earth's climate changes, it changes with particular spatial patterns. And so the way that noise is eliminated from these tree ring records is by accepting the temperature changes from records that are coherent in some way that's recognizable from the way we have, the way the climate works today, and calling that real information. And then if there's some weird wacko record here that does something totally different than everybody else, it'll get excluded from this sort of a method. So it's not a secret, but there is a problem with the tree ring data, and that is that in the most recent few decades of the instrumental record, starting from about 1970s to today, the temperature as measured by thermometers has gone up, but the tree rings don't show that. And it's not clear why that is. It could be because rising CO2 concentrations actually fertilize the trees in some way. It could be because one of the components of acid rain is nitric acid, which is nitrate, which is a fertilizer. So maybe fertilizer deposition has impacted the tree ring, the fidelity of the tree ring method. So does this destroy our confidence in the tree ring method to put together ancient climates? No, it doesn't destroy it. It undermines it a little bit. Like I said before, these proxy measurements are, they are what they are. They're as good as they are, and we have to use them with some caution. If we could actually have thermometers from 1,000 years ago, that would be better, but this is what we have. It's possible that there's a cap on the sensitivity of the method. We have to live with that possibility. Another form of proxy temperature measurement is called borehole temperatures. So what you do is you drill a hole in an ice sheet or in a soil column, and you measure the temperature as a function of depth. And what is happening with the temperature is that it's in the equilibrium, if the temperature at the surface stays at a constant value for a very long time, the temperature will just increase with depth because of the generation of heat in Earth's surface. This is called the geothermal temperature gradient. The temperature goes up by about 30 degrees centigrade per kilometer in the Earth, and more or less. So then if you have a sudden change in the temperature at the surface, it takes a while for that news to diffuse down into the ice core or the rock column that you're measuring. So what would happen to the temperature inside is initially it would only know about the warming right up at the surface, and then as time passed, the temperatures would relax toward a new equilibrium where it's again along the geothermal gradient, just going monotonically upward from the surface condition. So if you go out and you measure the temperature today and you happen to see something that looks like that, you can use what's known as an inverse method to try to back out how much the temperature changed and when. It's called an inverse method because while reality goes from cause to effect, the change in temperature at the surface leads to this distribution of temperatures below. The inverse problem has to go the other direction and go from the effect, which is this snapshot of temperatures in the boreholes down inside the ice sheet, and sort of back out what the cause was, how much the temperature changed and when. So in general, borehole temperatures give you a much smoother estimate of how the temperatures change with time, because if the temperature changes just a little bit, there's fast temperature changes here, you'll never see that down in the interior. So basically what you see is the longer time scale overall patterns, as we'll see when we put this together. One of the real workhorse paleotracers, and one of the very first to be developed, was based on what are called isotopes, which are different elements that have they're the same element, but they have different masses. So oxygen 18 has 2 more neutrons in the nucleus than oxygen 16. A neutron doesn't have any charge, so it doesn't mean that you have to have more electrons. The oxygen 18 and 16 have the same number of electrons, so that means they have the same chemistry. They're both oxygen, but they have different masses. And different processes in the hydrological cycle tend to separate these 2 isotopes. And so we can measure the relative abundances of the 2 isotopes either in calcium carbonate on the seafloor or in ice to get clues about how the Earth worked at earlier times. So the planet acts like a giant still, sort of distilling the light isotope to form the great ice sheets. When water evaporates, it tends to favor the light isotope because the lighter one can go into the vapor phase more easily. And then as that water, the vapor, gets selectively rained out, the rainfall tends to choose for the heavy isotope. And so that means that the water vapor that's left in the atmosphere as you go further and further north, where it's colder and colder, tends to get lighter and lighter and lighter in its proportion of oxygen 16 to 18. Until finally, when it forms an ice sheet, the ice sheet is very light. So by very light, I mean something like it has 5% less oxygen 18 relative to 16 of what the ocean has, which doesn't sound like a huge change, but it actually is a very large change, very easy to measure. And the way geochemists describe this is to do it in per mil instead of percent. So 5% is the same as 50 per mil. And the fact that it's lighter, they put a minus sign there. So the ice sheets have an isotopic signature of minus 50 per mil relative to the ocean, which starts out at 0 per mil. And then when you take enough water out of the oceans to make this isotopically light ice sheet, the water that's left behind is a little bit enriched. So it turns out that the ocean can be about 1 or 2 per mil heavier during a time when there's a lot of ice on the Earth. So we can measure the oxygen isotopic composition of the ice just by putting it in a mass spectrometer and counting the different kinds of atoms. But we can also figure out what the isotopic composition of the ocean was in the past from sediment cores by looking at the oxygen in calcium carbonate. So here's an equilibrium reaction where we're changing this heavy oxygen for the 2 light oxygens in this calcium carbonate here. And it turns out that which chemical the oxygen isotope, the oxygen 18, wants to be bound to depends on the temperature at which the calcium carbonate forms. So it's actually a bit of a trick, because measuring the proportion of oxygen 18 to 16 in calcium carbonate in sediments today, there could be a component of signal that comes from the global ice volume that can tell us about the shrinking and growing of ice sheets through the ice age. But it can also be a function of the local temperature, because when you change the temperature, it changes how the oxygen wants to be distributed here. So no paleoproxy is ever used in isolation. There are other proxies that can be used to help constrain and pin down the local temperature, for example. And then from suite of many of these tracers, we can begin to put together a picture of the world in the past.